we're asked to evaluate along the curve, and we see the circle here, which means it's a closed curve. Really, it's a closed and oriented curve. F dot dr. And if you're not comfortable with this notation, just remember this is the same as F dot TDS. There's a couple ways to write this. And what's our curve? Well, it's a square loop in the xz plane, centered at the origin with side length 2. And it's shown here, so we're going this way. And the function f of x, y, z is 2z cosine xy 3x. And we're asked to find, okay, what's the value of this? And we have some options given. All right. Do we have an answer? Sorry, what? I'm not saying you're wrong. I'm just saying I have bad hearing. The answer is 16. I don't think that's an option. E? 20? Bold choice. Okay, so let's think about this. What does this feel like? Someone said Green's theorem. It has like the feeling of Green's theorem. We have a closed curve. Green's theorem is set in the plane, but it's set in the xy plane, not in the xz plane. But it feels like Green's theorem. But we're sort of in space now. We're in three-dimensional space. So what's the three-dimensional version of Green's theorem? Stokes theorem. Now, Stokes theorem has surfaces. What don't we have? We don't have a surface. So can we apply Stokes theorem? Yes. We can apply it if we do what? Bring our own surface. Okay, so we have a curve. What's a convenient surface for us? Yeah, we're not going to be silly and make a complicated surface because we like ourselves. So we fill in and say, here's our surface. Now, we need to know the orientation for this surface. It's perpendicular to the y-axis. That's not enough to know which side is the top and which side is bottom. We need to know the normals. So which way do you go? In the positive y direction or in the negative y direction? And how do you know? Are you positive? Are you sure? How do you know? Yeah. You just imagine that you're a little person standing on this surface. And if you were to walk next to the edge, if you were standing on it, is your region to the left. And it is. So good. So that says the normal is 0, 1, 0. So now apply Stokes theorem. And what do you get? The answer is B. All right. So we had our normal. We filled it in. So you need to find the curl. So we're doing a curl computation. And we really only care about the middle entry because that's the only one that's going to come into play with the dot product. So middle entry, you have j partial z of 2z. That's where your 2 comes from. J partial x of 3x. That's where your 3 comes from. But you have to remember there's sign changes. So in one direction you add, one direction you subtract. So it's a 2 minus 3, which makes it a minus 1. I really don't care about this entry, but I'll put it in. And so lo and behold, we're integrating -1. But integrating -1 is nice because it just says, hey, just pull the -1 out. And then you're integrating s dsa, which means you're finding surface area. Or just the area of a square. It's a 2 by 2 square. So the area is 4, giving us -4. All right. So there's that problem. And this came off of an old final. Now, I know you're thinking about finals. Maybe you are. Maybe you should be. And we've told you, well, the more you fill out the survey, of course, the more you'll know. But I'm not going to be coy. You should know 2 of the questions that are going to be on the final. And what is one of them? So what should you make sure you understand? Good. You may say, well, what's the other one? Give me a few minutes. We'll get there. First, we got to practice Stokes. All right. Well, we still have to have our thought for the day. So here we go. Becoming fearless isn't the point. That's impossible. It's learning how to control your fear and how to be free from it. This is a quote by Veronica Roth. And there's a reason I chose this quote. We'll talk about that in just a second. But I do like what this is saying. You know, you may think, eventually I'll be completely in control and I'll have no more nerves. I still get nervous. And so no matter how long you do it, you'll get nervous. So you won't completely overcome it, but you can learn to control it. And you'll gain confidence and you'll be able to calm down and do better. Now, let's see how well people know. Well, I don't want to say where this is an author. What books have they written?
Divergence Theorem.
Ah, wow. Yes. So that was a reason I chose this. Divergent. Interesting. What's coming up in the near future? All right, good. So that's the second thing you have to learn. But we got to practice Stokes Theorem some more. So, okay, just a quick recap. This was what we talked about last time. It really is Green's theorem in space, which says if you want to integrate along the curve, when the curve is the boundary of a surface, then you can say, I can integrate over to the surface the curl dot n. And then most of the statement's just saying, hey, there's orientation. Orientation matters. Pay attention to orientation. And then we said, hey, you know what? There's really three ways to do this. You actually do the line integral, or you actually do the surface integral, or you be smart and you do the surface integral, but with a better surface. So when you can, choose a better surface. You can't always, but if you can, you should choose a better surface. All right. So that's what we learned last time. We should do at least one more practice. All right. So let f equal 3x minus y, comma 2z, comma 4x minus z. And let c be the path from 2, 0, 0 to 0, 3, 0 to 0, 0, 2 back to 2, 0, 0. Find the integral along the curve of f dot t ds. Okay. All right, well, let's see if we understand what's going on. So let's draw a quick picture of what our curve is doing here. So here's our space, our x, y, and z. And we'll mark some points here. 2, 0, 0, so this is you go 2 in the x direction. So here's 2. To 0, 3, 0, that says you go 3 in the y direction. So we move here. And then we're going to go to 0, 0, 2. So that's 2 in the z direction. So we move there. And then we go back to where we started. So here's our curve C. And we're asked to find the integral along the C of f dot t ds. Now we can, of course, find it. We could do it the old-fashioned way, which is to say, well, we can think of this as 3 line segments. We can parameterize each line segment. And then for each line segment, we can carry out the computation. But that's not our goal. Our goal here is to say, whichever way they gave us to do the integral is not the way we should do it. So if they ask us to do a line integral, we should do a surface integral. If they ask us to do a surface integral, either do a line integral or do a surface integral with a better surface. So let's use our tools. So here what's our tool? Well, we can use Stokes Theorem and say, I can think of this integral along this curve of f dot t ds. So this is our Stokes. This is equal to the integral over some surface f, curl of f dot n dsa. Now, we have the same problem as before. There's not a surface here. So what do? We bring one. Which surface do we pick? The triangle, right? Just fill in the triangle. Now, is that the only surface? No, there's infinitely many surfaces you can pick, but you always pick the simplest thing you can. Okay, so suppose we pick our triangle. Now, if I have this triangle, can you think of what surface we're actually capturing here? Like, can you describe this surface?
Plane.
It's a plane. It's a piece of a plane. So it's like, okay, so let's describe our surface. So we have a plane. Now, which plane is it? Well, the good news is we have 3 points. We could spend a lot of time figuring that out, or not. Which do you prefer? The not. Okay, good. Here's the fun thing. When you have points that are on the axes, it's actually very quick to fill in. They always will look like, excuse me. All right. AX plus BY plus CZ equals 1. And we're just going to find A, B, and C really quickly. Now, how do you find things? What should you do? Plug points in. This point, that's x equals 2, y and z equals 0. So 2a plus 0 equals 1. So what is a? Half. Plug that point in. X equals 0, y equals 3, z equals 0, 3b equals 1, b equals 1/3. Plug in that point. X and y are 0, and z is 2. That gets us the value of c. c is a half. So you end up with x over 2 plus y over 3 plus z over 2 equals 1. Okay, so there's our surface for our plane. And you'll notice that these numbers, 2, 3, 2, are these denominators. Not a coincidence. So if you happen to know all your points, your 3 points that are on the axes, it's very quick to find a formula for the plane. Okay, so we have our plane. Good. We have a formula for our plane. Great. What do we need to find next? Curl. All right, so how are we going to find that? Well, we'll just do the computation. So we should get comfortable with computing curls. Del cross F. We have our I, J, K. We put in our dels, which is our derivatives. Partial x, partial y, partial z. And then we put in our entries for F. 3x minus y, 2z, 4x minus z. All right. And now we start doing our downs and our ups. So going down, I, partial y of 4x minus z. 0. There's no y terms. Well, that's convenient. J, partial z of 3x minus y. So what's the derivative with respect to z of 3x minus y? 0. Then we have k, partial x of 2z, which is 0. All right. Don't worry, it won't all be 0. We'll have to do work, I think. All right. So those were going down and start going up. So we're taking partial y of 3x minus y. Minus 1. And so we're going to subtract, because we're going this direction, minus 1, and that's attached to k. Okay, partial z of 2z is 2. And that's attached to the I. So we're going to subtract 2 times I. And the last one, we have partial x of 4x minus z, 4. And that's in the j direction. So subtract 4j. So we end up with minus 2 minus 4 plus 1. So there's our curl. All right. So updating. We now know what we need to compute. We need to find the integral over S of minus 2 minus 4 1 dot n dsa. Now there's two options that you could take. One is that we could try to figure out n. We could do it, wouldn't be too hard. Take the dot product and then try to figure out the area of the triangle. Again, we could do it. Or we can think of this as a surface integral. This is a flux through a surface. So if you only see a vector valued function dot n, that's computing flux through a surface. How do we compute surface integrals? We push down into the xy plane. So there's this region in the xy plane that we want to compute. So let's see, where can I write this down? The integral on a surface G of, I'll say, MNP dot little n dsa, and where G, this is z equals a function f of xy. Do you remember what the formula is? It's equal to the integral over the region of the surface in the plane, stuff, dA. The real question is the stuff. Minus m fx minus n fy plus p. Okay. So we have our m and p. That's cool. What's our function f? It comes from the surface. So you're going to take your plane and solve for z. So you get z over 2 is equal to 1 minus x over 2 minus y over 3. Multiply through by 2, you get z is 2 minus x minus 2/3 y. So there's our f in the corner. Okay, so here we go. We're almost there. So we have, this is equal to the integral over our region R. We'll come back to that in a second. Minus m, negative 2, f sub x, which is negative 1. Subtract n, negative 4. Whoops, there's a negative there. It's a very weird place, but yes, it's there. F sub y, negative 2/3, plus p, and dA. Well, okay, there's a whole bunch of minus signs. So there's 3 minuses, so this really becomes a minus 2. There's, again, 3 minuses, so this becomes minus 8/3 and a plus 1. Okay, minus 2, minus 2, minus 8/3, plus 1. Get a common denominator of 3, minus 6/3, minus 8/3, plus 3/3. All together? The negative 11? All right. Cool. Negative 11 thirds. I can believe that. All right, so it's negative 11 thirds dA. So this becomes negative 11 thirds times the area of R. Because you're just integrating, that constant come out. That constant of negative 11 thirds comes out. So we're down to saying, what's the area of R? We didn't actually specify R. It's that triangle. What is the area of that triangle? 1/2 base height. What are our base and our height? Yeah, we can think of this as our base. Think of this as our height. So the area of R is 3. So what's our final answer? Negative 11. And we're okay to have negative numbers. That's perfectly fine. So negative 11. That was good. Got to review a couple of ideas. Any questions? I see at least one. Yes? You're right. We should have talked about that. Is it an upwards N?
Yes.
How do we know? We didn't check. We should have checked. We can check now, and then if it was a downwards N, we could fix it. So we can see the orientation on C, and as someone said the other day, is this just right-hand rule? Yes, it's just right-hand rule. You can imagine that you want your fingers to be pointing in the direction of C, then you curl, and wherever your thumb points, that's up. And so we're staying on the top side of the surface. So the Z component has a positive orientation. You're right, we should have checked that. Thank you. All right. Cool. Okay. Are we good with Stokes for now? Oh, I see more questions. Yes.
How did you know that AX plus BY plus CZ is equal to 1?
Because I've done this a lot. It's just a very convenient way to do it. Essentially, any plane that, as long as you don't cross the origin, can be written in the form AX plus BY plus CZ equals 1. But what I really was doing was, I know that because this happens so frequently, many times we'll see planes where we have 3 points that hit the axes. And so once they hit the axes, I didn't want to jump to here without explaining why. But basically I was like, aha, I know what's coming. And so making this 1 was very convenient. There's other ways we can do that.
If instead of going to that triangle on the XY plane,
Right?
if you just kept the normal vector n, would you just take the normal vector from the plane and then...
Right. So alternatively, we could have done the following. So let me grab, since we're almost out of space here. I'm not claiming this is a better way to do it, but I am claiming this is another alternative we could have done. So can we find the normal vector to our plane? Well, because I've covered up the plane, so the plane was x over 2 plus y over 3 plus z over 2 equals 1. What's the normal vector? N. Now you have to be careful here. But let's just start with baby steps. What's a normal vector? Right. So to this plane, how do you read off a normal vector to a plane? Coefficients. Okay, so reading off the coefficients, you get a half, a third, a half. Now, is this n, and why not? Right. We have to make it length 1, and we possibly have to fix orientation. We're okay with orientation. We already said, the z component should be positive. So we need to make it length 1. So we need to scale it. What do we need to scale by? Well, find the magnitude. So that's 1/4 plus 1/9 plus 1/4. And common denominator here would be 36. So you get 9 plus 4 plus 9 over 36. And 9 plus 4 plus 9 is a number. I think it's 22. So we end up with square root of 22 over 6. Now, that's the length. So what do we want to do? We want to say that our n is 1 over the length, 6 over the square root of 22, times this vector 1/2, 1/3, 1/2. If you multiply the 6 through, you get 1 over square root of 22 times 3, 2, 3. Okay, so that's n. So we could have said, hey, we're at the point where we knew we had the integral over our surface, so we could now say, aha, this integral over our surface becomes the integral of -2 minus 4, 1, dot, 1 over root 22, 3, 2, 3, dsa. Well, 1 over root 22, dot product, we'll get -6, -8, plus 3. -6, -8, plus 3, that might sound familiar. What does that give us? -11. So this becomes the integral over our surface of -11 over square root of 22 dsa. Well, you can pull out the constant, and then you have the integral over your surface of dsa, and that's the area of the original triangle. Now, how do you find that area? Do you remember how to find areas? I mean, we're at the end of the semester, right? We should know everything. Oh, walk down memory lane. Maybe it's not the worst thing in the world to do it this way. Okay, so here's 2, 3, 2. If you want to find the area of a triangle, what tool do you use? Does anything cross your mind? Cross product. Yeah. And you're like, ooh, ah, oh. Yes, the excitement builds. Okay, so we take two vectors, pick two sides. These are not the same orientation. We're just picking vectors from corners to corners. So this vector here, we go down 2 in the x direction, up 2 in the y, no change. Oh, whoops. Down 2 in the x, no change in y, up 2 in z. Here we go down 2 in x, up 3 in y, no change in z. So we have to take -2, 0, 2, cross -2, 3, 0, just when you thought you were done with cross products on this problem. Let's see. I'm kind of curious if we're going to get the same answer. I'm invested now. I want to know. I mean, I have predictions for how much area will be, but I want to know. Okay, so I, j, k, -2, 0, 2, -2, 3, 0. We have 0i, -4j, -6k. Other direction, 0k, -6i, and 0j. So we get up with -6, -4, -6. Now, if we were paranoid, what would we do to check to see if we did it right? Yeah, dot is something we should remember, right? So you just check the dot product if these are perpendicular. 12, 0, -12, okay, that adds to 0. 12, -12, 0, that adds to 0. We're all good. Now you might be saying, wait, what? You're checking perpendicular with the original vectors. That's how you check if a cross product is right. Now, is this the area of a triangle? No, not even close. It's a vector. A vector's not an area. So how do you get to an area? Magnitude that. All right. So we're going to take 1/2, because you have to have that triangle is half a parallelogram. Cross product actually finds area of parallelogram. So 1/2 the magnitude of -6 -4 -6. Now, we can do something to make it a little bit easier on ourselves. Do you see any common factors in -6, -4, and -6? 2. And even -2, right? We can pull that -2 out. Absolute value of -2 is 2. So this is 1/2 times absolute value of -2. That's the common factor. And then 3, 2, 3. So 1/2 times absolute value of -2 equals 1. Okay, so this becomes the square root of 9 plus 4 plus 9. Square root of 22. Put that in there. And what do we end up with? Now, does that look familiar? It's the same thing we had before. Which way was better? I don't know. Whichever way gets you to the answer. We're not testing on which way you chose. We're testing on did you choose the correct way. So anyways, yes, you could have found n. That was a very long digression. Other questions? Okay, all right. Well, I think we'll pause there for Stokes. We probably will have more practice with Stokes next time. So let's see. Where are we at? Have to go dig deep down here. So basically, where we're at is we're doing variations of the fundamental theorem of calculus. So we started with line integrals, and we said, you know, if you were integrating along a curve, a gradient of f, so this is our del operator, and essentially you should think of it as the del operator is variations of derivatives. So if I'm integrating a derivative along the curve, I can just evaluate the function at the end point. So you take the function at the end of your curve, subtract the function at the start of the curve. Now, if you think about endpoints are your boundary of your curve. So it's like, oh, I'm taking information about what's happening on my boundary with the function. That gives me information about a sum total of the derivative of the function along the interior. And then we went and we said Green's theorem. Green's theorem is something very similar. We can integrate over our region in our xy plane, partial n partial x minus partial n partial y dA. That's the same as integrating the boundary of our region, m dx plus n dy. But again, the integral over our boundary, that's what we have on the right, is the integral over the interior of the derivative. There's some sort of derivative involved here. I'm skipping orientation because otherwise that fills up a page. So we'll assume we have orientation. And then we said, we can do Stokes theorem, Green's theorem in space. Or if you like this, Green's theorem is a special case of Stokes theorem, which says if we want to integrate on the interior, we can do the curl. So that's, again, using that del. The flux of the curl through our interior is the same as the integral on the boundary of f. Now, if you remember a while back, how did we sort of motivate our Green's theorem? We said, well, suppose you have a closed curve. We said, if we have f equals gradient of f, and we have a closed curve, so in other words, we have something like this, f dot dr equals what? Do you remember what this became? Zero. Yes, the age-old strategy. If a professor in a math class asks a question, it's likely 0, 1, or somewhere on the board. What happens if it's not a gradient of f? Now, of course, you can still apply it. The integral along the curve f dot dr, what did that lead to? This led to Green's theorem, which is suspiciously written in red. I should have planned better. All right. So now let's ask a different question. Suppose I don't have a closed curve, I have a closed surface. A surface with no boundary. Okay, so that's what a closed surface means. No boundary. If I have del cross G, so it's a curl, and I integrate f dot n on this surface, what happens? And why does it happen? So what happens? 0. Why does it happen? So one way you can think of it, what's an example of a nice closed surface that we all are comfortable with? Let's think of a sphere. So here's our surface. So here's S, our surface. Now it doesn't have a boundary, so you know what we can do? We'll just add a little boundary. Here's our boundary. It's a surface where it has a single point as boundary. Why not? So now that it has a boundary, apply Stokes Theorem. Because it's a curl. So it says Stokes Theorem says it's the integral on the boundary of your surface, a single point of g dot t. But how much is a curve integral for a curve that has no length? 0. So we know that case, and this follows from Stokes. But what happens if it's not a curl? All right. Well, sort of our idea was to say, hey, you know, if it's a curl, it's kind of acting as the right-hand side. So now, if it's not a curl, we want to sort of move it into the other side. So in other words, we want to think about this as being the boundary of something. What does a closed surface act as a boundary of? A volume, a shape, a solid. So that's the idea. So here we go. This is Gauss's divergence theorem. It's this part right here. And I want to say this is not completely without precedent. We did mention that there's a flux version of Green's theorem. So if you look at the flux version of Green's theorem, it says more or less the same thing in the plane. So Gauss's divergence theorem. If you have a solid in 3D space with a boundary, so that's your boundary, so that symbol that looks like the partial symbol as the boundary symbol, and you have normals that point out from the solid, then the integral over the boundary of the solid of f dot n dsa, so this is computing the flux of your field through your solid, so how much is coming in and out of your solid, is found by integrating over the whole solid the divergence of f dv. And divergence, you might remember, that was why we had our quote, this is our del dot f. And this, by the way, is our happy one. Because del dot f, the divergence, is the easier one to compute. So that's the result. Okay. We'll give ourselves a second to process that, perhaps. And again, going back to the final, I said there's 2 questions you should know. We already mentioned Stokes. The other one is divergence. Now, you might be saying, how do I know if something is a divergence? There's kind of 2 ways you can tell. One is they'll say, use the divergence theorem. They're not always that clear. So I'm going to give you another clue. If you see this word, solid, and you see this computation, then it's divergence. They always will give it to you as compute this, and you say, ha, 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 I'm computing that. So it's in applications that we will see, we always move in this direction. So if you ever see a solid and you're computing f dot n on the boundary, you know it's divergence, you know what you're going to do. All right, let's see, we have time to do one. Yes, 1. Are we ready? We'll leave it up here for reference. I think we can squeeze it in. So let G be the surface. X squared plus y squared plus z squared equals 1 with normals vectoring out, so away from the origin. X squared plus y squared plus z squared equals 1. What surface is that? Sphere. Can you tell me anything else about this sphere? Radius 1, centered at the origin. Okay, so we have our sphere, radius 1. It's a happy sphere, and our normals are pointing out. Okay, so we're asked to find the integral over our surface, which is our sphere, of 2x, comma yz, comma z squared dot n dsa. Well, let's use our tool. What is this going to be equal to? Triple integral over the sphere. Let's give the sphere a name. We'll call it D. So D is our sphere. So we're filling up our sphere. There's our sphere. D equals unit sphere. Okay, now we have to compute the divergence. So this is our F. What's our div F? Do you remember how to take divergence? 2. Take derivative of the first term with respect to x, derivative of the second term with respect to y, derivative of the third term with respect to z. So it's the integral over our sphere of 2 plus 3z dv. Okay, so that's the integral over our sphere of 2 plus the integral over our sphere of 3z. Now, one of these integrals we can do quickly, and the other one we can also do quickly. Which one should we do first? The first integral. Okay, the first integral is doing what? It's almost volume. 2 times volume, right? So how do you find the volume of a sphere? 4/3 pi r cubed. Do you have to memorize that? Nah, we'd give it to you. We're nice. So don't stress it like, oh my gosh, do I have to remember the formula for a sphere? Memorize these formulas. That's what we want you to know. Okay, so the first is 2 times the volume of a sphere, 4/3 pi r cubed, 1 cubed. Okay, so that's the first integral. The second integral, what is that? I claimed it was easy. Why is it easy? What's the answer? It is certainly an odd-looking integral. In some sense, yes. So there's symmetry, so that if I have a point here where there's sort of x, y in a positive z, I can match it down below, x, y in a negative z. What does that help me to do? It all cancels. So it's 0 by symmetry. So we get 8/3 pi. So this is odd symmetry. That's what helps us knock that out. Now, if you didn't know it was odd, we could have, of course, gone and done the whole computation, and we would have gotten the answer, and that would have been fine. Any questions on this one? I see I have a minute left. We can do one more, or we can guess one more. Okay, suppose you see a problem like this. You see the word solid, you see the dot n integral, you know it's divergence. So you can, in your head, quickly, let's compute the divergence. What's this derivative? Negative 2z. How about here? 2. How about here? Okay, so negative 2z plus 2, 2z minus 3. The 2z's cancel. 2 minus 3 is negative 1. So this integral is going to become what? Negative 1 times the volume. What's the shape? Do you recognize it? It's a cylinder with a hole down the middle. So you end up with negative 1. The volume is 3 pi. It's negative 3 pi. It can be that quick. And it really can be. So don't stress. Use the theorem. All right. Thank you. Have a good day.